In this video, we're going to go over the type of vector application that is sometimes just straight up called an airplane problem. These sorts of problems tend to give students some troubles, so we'll try to, in this video, address what those things are and get you to the point where you can do them correctly right away. So there are going to be the three examples in here. That's going to make for a fairly long video, so if you feel like you only really need to watch one of the examples to get an idea of what's going on, then that's fine. But in the course of those three examples, we'll hope to kind of cover all the different little twists that might happen in these kinds of problems. So let's look at the first one. Okay, there's an airplane that needs to be traveling at 700 kilometers per hour on a bearing of north 55 degrees east. There is a 70 kilometer per hour headwind blowing south 80 degrees west. What should the pilot set her airspeed and bearing to? Okay, so what we have here, and it's very important, this is the most difficult part a lot of times of these kinds of problems, is to identify what's happening in the problem and then what's being asked. And the best way to do that, I think, is to draw a picture with the vectors on it. So what we're going to do to start is draw a little you can think of this as like a little compass. It's just a plus sign. Actually, let me give myself a little more space. Okay, I'm going to do actually a good job on this. Okay, I've got, essentially this is just a coordinate plane. Think of it like the origin. Okay, now it needs to be traveling, this airplane, 700 kilometers per hour on a bearing of north 55 degrees east. So let's draw that vector in green. And we could just do a reasonably okay job of drawing it. So the magnitude of this vector is 700. And the bearing, and now remember, the bearing is an angle measured off the vertical. So that angle right there is 55 degrees. That is north 55 degrees east, right? East, north, west, south. Okay, so there's the vector that we're trying to get. However, it turns out that there is a headwind blowing south 80 degrees west. So if we make another little compass thing at the end of our flight path here, or the end of that vector, and we drew another vector, let's draw this one in red. Starting there and going south 80 degrees west, it's going to go something like this, okay? So that right there, that magnitude is 70, and it's at an angle with this, so an angle with the vertical here, like all the way to there, that angle is 80 degrees south, 80 degrees west. Okay. Now, what we have to identify is that if the pilot did nothing, let's say the pilot set the airspeed to 700 kilometers per hour at that north 55 degrees east bearing, that wind, the way we add vectors, that wind would have ended up would make this airplane end up right there, which is not where it needs to be, right? And so in order to get to the right spot, where should the pilot have aimed the airplane, and how fast, what airspeed should the pilot have set off at? And so what we have to do is say, all right, in order to accommodate for this wind, what if I had that vector over here instead? Okay, so instead of then, if I aimed, so let's draw another line. If I had my vector that I want, let's do another color here. This here in yellow, this is going to be the vector that I should have targeted. If I aimed for this point right here, the wind would blow me back to the right spot where I wanted to end up. So here we have our vectors, okay? We don't want this little red, we don't want this little red one off to the left here. We want to have only those three, okay? So it's kind of hard to tell them. Let me draw them then. The orange one's okay. The red one is this one, okay? That's the wind vector, and then the green one is the airplane. So we wanted 700, so this is good. This north 55 degrees east and 700 kph. That's the one we wanted. But in order to get that, we're gonna need to have set off at this orange one. And so the information about the orange one, that is the magnitude, which would be the ground speed. Sorry, actually the airspeed, right? Because the pilot's going to set their airspeed to it's going to be far higher. It's going to be greater than 700 because the wind's going to blow them back and make them slow down. And the direction and that bearing. So that's what we're trying to solve here. And the way we're going to do it is by breaking down each of the two component vectors of our orange vector, which means the green and the red vector. We're going to break them down into horizontal and vertical components. So basically, we're just going to draw these big right triangles all over this, and see if I can do this in like a smaller thing. So here's the horizontal component of the green vector, and here is the vertical component of the green vector. Okay, cool. And now the red vector, same thing. Here's the horizontal component of the red vector. Here's the horizontal component of the, actually it goes the other way, right? Here's the horizontal component, and here's the vertical component of the red vector. So if we can add up all of these, all of that length right there and that length right there, like that will give us the horizontal component of the orange vector. And if we can add up this vertical part right here and this vertical part right here, that'll give us the vertical component of the orange vector. With that information, then we can find out everything we need to know. So what we'll do is we will start to label some things. So I know that this angle right here is 55 degrees. So I know that this angle, the complement to that 55-degree angle, is 35 degrees. So if I call this angle theta right here, right now this is our angle theta, that means that this horizontal component of the 700 degree, like what we want, is 700 times the cosine of 35 degrees. And the other side would be 700 times the sine of 35 degrees. Okay, amazing. Now all we need to do is find the same information about this red vector. So this angle right here, okay, this is a little bit tricky because we know that that red vector is 80 degrees off of the vertical there, right? So if we know it's 80 degrees off the vertical, that means it's 10 degrees off the horizontal. So this angle theta over here is actually 10 degrees. So we'll write these components. This side of length right here, the side, kind of a side length of a triangle, right, is 70, because this magnitude is 70. 70 times the cosine of 10 degrees. And then that means that this is 70 times the sine of 10 degrees. Okay, great. So now the sum of all the horizontal components, and if we want to, we can use I hat and j hat notation here because they're vectors, but we can say that 700 times the cosine of 35 degrees plus 70 times the cosine of 10 degrees, I hat, plus 700, actually, you know what? Yeah, we're good. 700 times the sine of 35 degrees plus 70 times the sine of 10 degrees, j hat, that is the horizontal and vertical components of this the vector that we want. So all we need to do is actually just plug that into a calculator, okay? And what we're going to do here is we're going to calculate this, and we're going to store it in the calculator as A. And we're going to calculate this, and we're going to store it into the calculator as B. Okay, and I'm just going to explain the rest of the math we're going to do before we actually plug it into the calculator. Because at that point, I will have the horizontal and vertical components of the vector that I'm looking for. Okay, remember that vector was orange, so let's just draw it again kind of in miniature over here. We had something like this, right? We're going to have this part of it and this part of it, and it's a right triangle. If this was A and this was B, well, A squared plus B squared equals C squared. C in this case would be the magnitude of the vector. That's one of the pieces of information I want. So we'll use the Pythagorean theorem. In fact, we can just say that the speed that I want, so like let's call this, it's going to be the air speed. Let's just call it lowercase a. Okay, I don't know why this is so big. Hold on. The magnitude of vector A, which we're going to call the airspeed, is equal to the square root of a squared plus b squared, right? That's what the Pythagorean theorem will tell us. Okay, then if you think about this also, we want to know, we're also going to want to know this angle. Okay, we're actually not going to want to know that angle. We want to know the complement of that angle. We want to know this angle because that's going to tell us the bearing that we should have set off on. Okay, so in order to do that, there's a couple different ways. We can say, let's find this angle and then just subtract that from 90 to get the complement. Or we can say, all right, well, this is, so the theta that we want, right? This theta is, we have, this is a rectangle. We just can draw a rectangle here, right? The opposite side of that rectangle is A, the adjacent side is B, when we're talking about this angle theta that we want. So with respect to this angle theta, the opposite is A, the adjacent is B. That will give us this angle if we say theta, the angle I want, is equal to the inverse tangent of A divided by B. And so well, this is the process. We're gonna put this into the calculator and store it as A. We're gonna put this into the calculator and store it as B, and then we're gonna perform these two operations, and we're gonna have the answer to this problem. Okay, so let's do that. Let's turn the calculator on. First of all, we need to make sure that we are in degrees mode. So we're gonna go check the mode, and it's in degrees. That's great. Okay, and then we've got 700. It's kind of difficult. 700 times the cosine of 35 degrees plus 70 times the cosine of 10 degrees, okay, is this, right? We're going to store that. You hit this STO button, and we're going to store it as a letter, and that letter is going to be A, okay? Enter. Now, anytime the calculator sees the letter A, it's going to think 642.3429, blah, blah, blah. Same thing for B now. 700 times the sine of 35 degrees plus 70 times the sine of 10 degrees. Okay, this is what B is. So we're going to store as B. Okay, now all we need to do is do these two calculations. So what is the square root of A squared plus B squared? Whatever that is, 764. Okay, so we'll go back over here. That was, that was, what was it? 764. 764 kph. That's the speed we should have set off on. This should make sense to you. It's faster than the speed we meant to go, right? We need to get to this place at a certain time. And in order to get there at a certain time, because of the headwind, we'll have to adjust our speed to go faster. All right, adjust our airspeed. Okay, next thing is we want to do the tangent inverse, right? So second tangent inverse of alpha A divided by alpha B. Okay, and that's going to give us 57.21 degrees. So this is 57.21 degrees. That's not quite it though, because we have to write this as a bearing. So it should be 764 kph at 57.2, north, right? North 57.21 degrees towards the east. And that is the answer to this. That's the airspeed and bearing that should have been dialed into the plane's computer before taking off. Okay, so that's that first problem. There's a few steps here. The hardest part, I think, is drawing the diagram. Okay, here's another one. The pilot of an aircraft wishes to head directly east, but there's a wind speed of 40 miles per hour blowing out of the northwest. If the pilot maintains an airspeed of 250 miles per hour, what compass heading should be maintained? Okay, what is the ground speed of the aircraft on its easterly flight? All right, so here's what's happening. The pilot wants to go east. So we're going to draw our little compass first, and the pilot wants to go east. Okay, and we also, there's a wind speed of 40 miles per hour blowing out of the northwest. So here is, let's blow out of the northwest. So out of the northwest means it's coming from this direction and it's going that direction. Okay, so the wind vector would be something like this. Okay. Now, we still want to go east, right? But the wind is going to blow us off course. So we need to actually aim up to be over here. So we need to aim over here, and it says that the pilot is going to go, his airspeed. His airspeed is actually going to be 250. Okay. Sorry, I'm all over the place with this drawing so far, but I promise you it'll make some sense in a minute. Okay, so the wind vector in this case is this orange one. The blue vector is the is the airspeed given to us. So 250 is the magnitude of this. Okay, and the 40 is the magnitude of this wind. Okay, and the last thing we have is we want to know the ground speed, right? So the actual speed, we'll call that vector g. Okay, vector g. What is the magnitude of vector g? We know, we already know that it's easterly. So what we need to know in this answer is what is g and what is this angle right here. Okay, those are our two unknowns. Okay, so no problem. We can do all this. Let's see. What do we do here? We can, first of all, we can say, we can break these components up into their, break these two vectors up into their components, right? So we can say that this, looking at the 250 vector, the one that goes up to the northeast, okay, these components would be, actually we don't know what theta is yet, right? So we'll have to work backwards to find theta. But we do know is that this here is 45 degrees, okay? That would be south 45 degrees east, or if I drew it from standard position, we'd have a 45 degree angle right there. We know that because if it says that it's straight coming out of the northeast, coming out of the northwest, that means directly out of the northwest, so 45 degrees to the corner, like. Okay, so what we can do, we definitely know about the vertical component here. Actually, let me see. How do we go about doing this? Okay, we would have. Okay, so we have the vertical component of this. We have this entire vertical component. Oops. The entire vertical component, because we know everything about this orange vector. We know its magnitude and its direction. So that means that this vertical component right here is 45 times the cosine. Sorry, it's not. It's 40 times the cosine of 40 times the cosine of 45 degrees. Okay, both this horizontal component and this vertical component are the same because it's a 45. It's coming out at a 45 degree angle. Okay, with that being the case, if you look at this larger triangle on the left, we have, and I'll draw it right here, we know that this is 40 times the cosine of 45 degrees. We don't know theta. We do know that this is 250. So we have two sides of a right triangle, and we can find the angle. And then we do that by saying this inverse sine, right? So sine inverse, arc sine, of the opposite side, which is 40 cosine 45 degrees, divided by 250, that's going to give us our angle theta. Okay, so that's great. We also know, and we'll come back to that in a second, but we also know that this length here is 40 times the sine of 45 degrees. Sine of 45 degrees, cosine 45 degrees, same thing. So really what we're going to find here, the goal here is two things. We need to find this length of this triangle, because once we do find that, oh, it's not drawing. Oh, sorry, hold on a second. Once we do find that length, we will we'll add it to our 40 sine 45. Okay, this plus this is going to give us the magnitude of vector g. So first things first, let's find that angle. So this is the answer to the angle part of this question. Actually, it's not, right? This is going to give us theta. This is going to give us the angle theta right there. We want, what we actually want, though, we actually want the complement to that. So let's find theta and just subtract 90 for this one. You could do it the other way around. You could flip these side ratios and you'll get the right answer. Because essentially this is the angle you're going to want to find and solve for. It's the same as this angle that's drawn. So let's do that. So we're going to say 90 minus the inverse sine. Oops, I didn't put the minus. 90 minus the inverse sine of 40 cosine 45. That's 75. 45 divided by 250. Okay, and hit enter, and that's going to give us a bearing of 83.5 degrees. So it's going to be north 85.3 degrees towards the east. That's the answer to the bearing. That's this. North 85.3 degrees east. Okay, awesome. Now we just need to find the angle. Now we need to find the side length, which we can do any way we want. Okay, if we have this angle, we can use trigonometry, or we can use the trig ratios. So we could say, for example, the complement. So actually, we kind of let's fix that real quick. We have the complement. Oh, mess things up. Okay, the complement of this angle, if we actually subtract 90 from this, that angle was really 6.49 degrees. Okay, theta was really 6.49 degrees. So let's use this angle theta to find this length. So if we say that, for example, the cosine of our angle theta, which we have in the calculator, is equal to the adjacent side, which we don't know, divided by 250, well then 250 times the cosine of this angle theta will give us the side length we want. So let's do that. We want the cosine of that angle times 250. Nope, that's times 10 because we've didn't type that right. 248.39. So this part of this triangle is 248.39. We're going to add that to our 40 sine 45. Man, my work for this is all over the place. But we have this 248.39, and we're going to add the 40 times the sine of 45. I'm writing this as rounded numbers in my work, but I'm still using the exact values in the calculator. 40 times the sine of 45 degrees. Hit enter. So 276.68. So this is equal to 200 and what was it? Oops, I just got rid of that. It was I think it was 276.68 miles per hour. So the answer to this then was that is the speed of its easterly path, because that's one of the questions that was being asked, and this is the heading that the pilot should have set out on at their airspeed of 250 miles per hour. Okay, so that's that one. Again, the diagram is the tricky part. All right, here's the last one. A pilot says the airspeed of 450 miles per hour at a bearing north 65 degrees east in order to arrive at his destination at scheduled time. Little does he know that all the farts in the world are blowing in from the northwest at a speed of 90 miles per hour and a bearing of south 10 degrees east. Just when he thinks he has arrived, he realizes that the farts blew him off course. What speed and bearing should he have set off at? Okay, draw the picture first. That's the biggest thing. Okay, so we want to go 450 at north 65 degrees east, so that's kind of probably off. Try to draw your original drawing as kind of to scale as possible to really help with your understanding. So let's go like about that. Okay, so this is 450, and this angle here is 65 degrees. That's the north 65 degree east. Okay, now there's all the farts in the world blowing in from the northwest. That means to the southeast. Okay, so that means going that way. And this magnitude is 90. Okay. It's not. It's a bearing of south 10 degrees east. So it's not actually directly from the northwest. Sorry about that. So south 10 degrees east means it's like this. Okay, where that angle is 10 degrees, and this is 90. So this pilot, if he was unaware of the farts, he would end up here, right? That he's off course. He's missed his target. So where should he have aimed in order to get to where he wanted to go? Well, just like the first problem, we should have aimed up here. So we actually are targeting this point right there. So the question then is asking, what is the magnitude of that vector and what is this angle off the vertical? Okay, so we want to know this angle theta, and we want to know the magnitude of this, which would be our airspeed that we wanted. Okay. All right, so this all we have to do then is break these vectors up into their components. So let's do that. We've got the the green vector, our 450 vector, if we go like that, that's our horizontal component, and that's our vertical component, okay? And then our fart vector, right, it actually has a horizontal component like this, and a vertical component like this. So something interesting to note here is that our resultant vector, this one, it's shorter than our, like in the horizontal, it's shorter than our original one. So we're going to have to subtract. We're going to find this and subtract this. So let's label these things. So we know if this was 65 degrees, and that means this is 25 degrees, right? Because they're complements. 65 plus 25 is 90. So that means that this is 450 times the cosine of 25 degrees. And that this is 450 times the sine of 25 degrees. Okay, for this little vector right here, I know that that's 10 degrees. So if I look at this, let's just keep that 10 degrees. With respect to this 10 degree angle, this opposite side over here, that means that's sine. So this is 90. So that means it's 90 times the sine of 25 degrees. And this one here would be then 90 times the cosine of 10 degrees. Why did I put 25? It's 10. Okay, so the math then sets up like this. If we're looking at the components of our big vector that we're trying to find, it works like this. We've got 450 times the cosine of 25 degrees minus our 90 times the sine of 10 degrees. That's I hats. That's the horizontal direction. Okay, plus, and in the vertical direction, we have 450 times the sine of 25 degrees plus 90 times the cosine. 90 times the cosine of 10 degrees. Notice the sine and cosines are switched. It only matters where your angle is. This is all dependent on the angle. It's not always the case that cosine is horizontal and sine is vertical. That's only the case on a coordinate plane when you're talking about your standard position angle drawn off the horizontal. So we just use the trig functions as tools. So we use whichever one we need depending on the situation. Okay, so just like the other problem, we're going to store this stuff in our calculator. We're going to store this, maybe. We're going to, I don't know if my battery's running low. We're going to store this in our calculator as A, store this in our calculator as B, and then we're going to compute those two things. So we're going to find, we want to know the airspeed, the magnitude of the airspeed is going to be equal to the square root of A squared plus B squared. And then theta, okay, this angle theta that we're trying to find, we're actually going to do inverse tangent of A over B for the same reason we did it in the last problem. Okay, because if you think of this big triangle here, okay, this is B, and this over here, this is A. So if I think about this angle theta, like I can kind of draw this over here. That's A. Ooh, that's not straight at all. Sorry, that's A. And that's B, right? It's just a rectangle. And then, with respect to that angle theta, the opposite side is A, the adjacent is B. So that's why we're doing it that way. Okay, so last step then is to plug these numbers in and figure it out. So we've got, we have 450 times the cosine of 25 degrees minus 90 times the sine of 10 degrees. Okay, enter, and we're going to store as A. Okay, great. Now we're going to use the other values, so 450 times the sine of 25 degrees, plus 90 times the cosine of 10 degrees, and we're going to store that in our calculator as B. Okay, so we have A and B. So to find the magnitude, we're going to do the square root of A squared plus, oops, I screwed that up, sorry. The square root of A squared plus B squared. Okay, so 481. So the ground speed of this, or the airspeed that the pilot should have set off on for this problem, 481.21 miles per hour at a bearing of, it was going to be north some amount of degrees east. So what is that? Let's see. Second tangent inverse of A divided by alpha B. There you go. 54. So 54.6 degrees. 54.59. 54.6 degrees east. Right, and that's it. So now the hard part here, upon reflection of these problems we've done, is getting the diagram right. Like, what is the problem asking? If you draw your diagram accurately, it's just a matter of breaking the vectors out into their components and doing some fairly straightforward trigonometry calculations. So hopefully this video has been instructive. If we will do more problems like this in class, if you have questions, please ask. Please think about what your questions are and ask them.